Okay, so let's go ahead and solve our first chapter 8 problem. Notice that we're going to start out by writing the differential equation down, and since this is an RLC series circuit, then we have the following. We have I double prime plus R over L I prime plus 1 over LCI equals, it's going to be 0 here. Now, it's true that this problem, the Vs is 0, but all we really need is the Vs to be any constant, and the derivative would give us 0, so we're good there. So we plug in the numbers that we have for this problem. So I double prime, my R here is 6 over L is going to be 6I prime plus 1 over LC, so that's going to be 1 over 0.04, so that's going to be 25I equals 0. And so we go straight to our characteristic equation, s squared plus 6s plus 25. And we quadratic formula this, negative 6 plus or minus the square root b squared minus 4ac all over 2a. And let's see here, that's going to be 36 minus 100 is negative 64, so it's going to be 8i there over 2. So we get negative 3 plus or minus 4i. And that means we now know I of t is going to be a1 e to the negative 3t cosine 4t plus a2 e to the negative 3t sine 4t. And so now we have to do all the work to find a1 and a2. Now notice that in this problem, they do tell us that IL of 0 is 4 amps, and since the current through the inductor is the same as the I of t we're looking for, that means that I of t is, I of 0 is 4 amps, which if you plug in 0 into this formula, the sine term is going to go away. The cosine term is 1, e to the 0 is 1, so it means we immediately find our a1. That was easy enough. The a2 is going to be the real pain. So if you know from Math 252, what we're going to do is we're going to take a derivative and use that to find a2. So what we need is, we need to know what the value of our unknown function is derivative at 0. That's a problem, because in our initial condition up here, they did not tell us that. They told us the voltage across the capacitor at negative 4. And okay, well, how are we going to compare that? Well, we know that for a capacitor, the current on a capacitor is C times the derivative of voltage across a capacitor. But the thing is this is the wrong formula, because this would work if we had the derivative of the voltage, but we don't, and we want the derivative of the current. So this is the reverse way around here. So we'll cross that out. And so if that one doesn't work, then we're going to use our inductor rule. So the inductor says that the voltage across an inductor is L times the derivative across the inductor, which is going to be just L times I prime, right? Because IL is the same as I for this circuit. So if we knew what our voltage across the inductor was at time 0, then we could solve and find the derivative of I at 0, but they don't tell us that. However, we do know that the voltage here is 0 volts. We know the initial current is 4 amps and the resistance is 6, so that means this is going to be 24 volts. And we know that the initial voltage across the capacitor is negative 4 volts. And so if I want to find out what my VL is here, I would do a little Kirchhoff's law here. I would have 0 plus 24 minus 4 plus VL equals 0. VL at 0. So VL at 0 then is negative 20 volts, which means my I prime of 0 is that divided by L. It's going to be, again, negative 20. Now we get to take the derivative of this fun stuff here. So I prime of t We have to use the product rule here. Negative 3a1 e to the negative 3t cosine 4t plus a1 e to the negative 3t times a negative 4 sine of 4t plus a negative 3a2 e to the negative 3t sine of 4t plus a2 e to the negative 3t for cosine 4t. And if I plug in 0 everywhere, all the sine terms go away, and I would have negative 3a1 plus 4a2, and this is supposed to equal negative 20, and I know what my a1 is. a1 is 4 again, so then you can solve here. That'd be negative 12, add 12 is negative 8, and so we're going to get negative 2 here. And so that means the final answer then is a1 4 e to the negative 3t cosine 4t, and a2 minus 2 e to the negative 3t sine 4t amps. So you can see you're going to have a lot of effort to find the a1 and a2. And I want to point out something here, that this problem, it fit on this one screen here because they gave us the initial values of both the inductor current and the capacitor voltage. And on future problems, they're not going to give that to us. And so on future problems, our first step is going to be to find those. And that's going to take a bunch of work. And then once we've found them, then we get to go back and do all of this again to finish the problem. So chapter 8 are in generally very, very long problems, and we will see that as we do more of them. But this is our first example here.